Hello, everyone. Welcome to DRP Colloquium. Today we have the pleasure of having Merve Bodur from University of Edinburgh. She is going to talk about two-stage stochastic programming, applications, and decomposition algorithms. Thank you.
Thank you very much for the nice introduction and for the invitation. It's a pleasure to be here. Thank you very much, everyone, for showing up despite maybe late evening. So I first want to introduce a little bit about, I guess, what I'm doing overall in my research main area, and then tell you a little bit about my specific expertise area of two-stage stochastic programming or in general stochastic programming. And thinking about the fact that you may not be familiar with it, my also motivation would be showing you all sorts of applications that you can do with this modeling framework, and as well as a little bit of methodological ideas. I would like to discuss how we efficiently solve these optimization models by means of decomposition algorithms. All right, so a little bit about myself, and some of you might have seen my name in some places, but for those of you who don't know, in 2011, I got my degrees from Boğaziçi University. I had a double major with industrial engineering and math. And then I directly went to the US for my PhD. Along the way, I also got some master degrees. So I graduated from University of Wisconsin-Madison in 2015. And then I moved to South, if I continue the path a little bit. And I did a postdoc for about 1.5 years in Georgia Tech, in again, industrial and systems engineering. And then I moved all the way back up to Canada. I worked there for about 7 years. And then a couple years ago, I moved to Edinburgh. And now I've been here for almost 2 years. So I'm working in the specific area of optimization. And especially today, I will tell you about this stochastic optimization that I'm especially spending time on. But also, I love to do applications. So in that regard, in my research portfolio, you can find all sorts of applications. And today, you will get to see some of them. So by the way, if you have any questions whatsoever during the talk, feel free to interrupt, just jump in. I don't have to cover all the slides that I prepared. Okay, so but overall, how I do research is I'm working specifically on the discrete and stochastic optimization. I will tell you all about it today, but my main focus is I love algorithm development, methodology design. So I am mostly developing fundamental algorithmic and theoretical ideas to solve some optimization problems, but also I do love doing applications. And actually, in that regard, to me, it's a very nice feedback loop between these two. You develop some methodological ideas and then you try to implement them in practice, help solving some of the problems of interest to some people at least. So you do applications which might lead to impact in real life, if you will. But then if you have some interesting applications inspired from the real practice, that will actually lead to very difficult problem structures that you will analyze, and it will lead to some more methodology development, and you do this feedback loop. They really work well together. And that's what I usually do in my research. So this is like not fully up to date, but just to give you a glimpse. So probably some keywords they got bigger a little bit now. But today, especially what I would like to talk about is this stochastic programming, and it is a subclass of optimization, of course. And I do work a lot about like multi-stage stochastic optimization, but today as a starting point, I will stick into two-stage stochastic programming models. And of course, the key would be we would like to have some integer valued decisions in our mathematical models, how to handle those. And of course, in order to solve these models more efficiently, we will talk a little bit about these decomposition techniques. All right, so let's start with optimization under uncertainty. So the only thing that is certain in this world is the fact that nothing is certain. And in that regard, in optimization under uncertainty, we are trying to develop mathematical models to help us, guide us for making decisions considering these future uncertainties we will be facing. And some of our decisions, they will have to take integer, in other words, discrete values only. So in that regard, it's going to be very important to preserve these discrete information for certain decisions. So let me maybe start with a purely continuous example, which is this one. So it's a very, very familiar example. That is this portfolio optimization. Say you have a certain amount of money in your pocket and you are trying to invest this amount of money, and you have a bunch of asset options that you can invest your money in. So how much of these specific maybe bond options or stock options or gold you should invest your money in, how to split it, right? Your portfolio into these various options. But then here, the important thing is, your objective will be maximizing your overall return, right? But the return, you are going to make the investments now, but the return is going to occur in the future. And that future, the return rates, what is going to be exactly the return of each of these asset options, it is uncertain. Based on the historical data, you might have some idea, but you don't know exactly if you put one, let's say, dollar to this option, is going to get you $2 back. There is no certainty. That's why you need to incorporate uncertainty about certain parameters associated with your own decision-making problem into the mathematical models. Hence, you make more informed decisions. And that's where this stochastic programming framework comes into play. So another very famous example would be this airline scheduling. Say you are trying to make a schedule for, say, Turkish Airlines for the day, but then, of course, there are a lot of uncertain parameters you can imagine. Most notably, the weather will lead to a bunch of delays for the flights. So while you are making the schedules, you may need to consider these potential weather impacts or any other uncertain parameter you can think of that will fundamentally impact the schedule, and accordingly create the schedule in a much more robust manner so that people are going to be protected if there are certain delays. So okay, we are going to talk about this stochastic programming, which will help us making better decisions, hopefully, considering uncertainty. But why this framework, it works? So it is all thanks to the availability of the data. So this slide is actually, I asked ChatGPT last year to give me these statistics, and ChatGPT claimed that, and then I double checked the fact afterwards. So it claimed that like this huge amount of data will be generated in 2024. This much data will be, I didn't even knew this like measure of zettabytes. It is giant amount of data will be generated in 2025. And then the most striking statistic has been for me is approximately 90% of today's data actually will be generated in the past 2 years alone. So we have an abundance of data, and why don't we leverage it, right? So for instance, here are a couple of examples, especially if you are doing research, you have great publicly available data resources out there as well. For instance, this one is taken from Public Health Scotland data repository, which is available to everyone. For instance, they have all the vaccination related statistics available on their repository. There is abundance of data. So then the question is, how can we leverage it for making better decisions? The idea would be we use this existing historical data to make informed predictions for the future and make our decisions informed about the future, because the consequences we will experience, the consequences of our decisions, we will experience them only in the future. So in that regard, more specifically, especially in the stochastic programming framework, what we will do is we will use the historical data to build some potential future scenarios. For instance, for our return of investment decisions, what might be the possibilities for the return? If I put $1 now, it could be $2, 2.5, 2.2. Based on the historical data, we will create these future possibilities and incorporate these future possibilities predictions into our decision-making frameworks, into specifically our mathematical models. So in a nutshell, here's the decision-making under uncertainty framework. First of all, as I mentioned, we would like to leverage existing abundance of historical data to model uncertainty. If these returns of our investment decisions are uncertain, you are going to first create a model of future uncertainties. And then you will embed them, incorporate them into your decision-making, the purple block. So here we will then, whatever decision-making problem you have at hand, you are going to create a mathematical model of it using these future predictions. And then the key will be, this is going to be usually difficult to solve. So you will do a little bit of math to develop some potentially problem-specific algorithms to solve these models more efficiently. And then once you have the solutions, you are going to go ahead and hopefully implement these decisions and live happily ever after with them. So more specifically, in this green block, we are going to use the historical data to model the uncertainty, which means we are going to create these possible futures of certain uncertain parameters using the data. And each option is, you will have like each option, what might happen in the future for your problem parameters, but also you will generate a potential probability of occurrence for that future scenario. And then in the mathematical modeling block here, the purple, we would like to primarily decide with the help of such models what we should do now, which decision I should implement. But as I said, the important thing is while we are making the decisions now, because some consequences we will experience in the future, we would like to consider the future possibilities of uncertainty. So the future we are going to incorporate into our models only as a guidance. The future decisions, you will make them when you find yourself there. But while you are making today's decisions, what you should do now, you should also provide an idea about what might happen in the future and accordingly what you might be doing in the future to make better, more informed decisions today. And then you will have an objective which depends as the decision maker how risk averse or risk neutral you are. All right, so let's start with this super simple example. So this is known as this news vendor problem. And suppose like your degree didn't pan out and then you decided to go out to the streets in Istanbul and then you are going to sell newspapers. So this is your job. And the important thing is you adopted this as your full-time job. So you are going to do this for a long term, say maybe 4 months, for a year, day after day. So this is your goal. So then there are these very simple decisions you need to make every day. How many newspapers you would like to buy so that you are going to go out to the street and sell those newspapers to people tomorrow. And of course, like your whole goal will be maximizing your profit. And there are only 3 parameters of interest in this simple problem. If you decide to buy 1 newspaper, you gotta pay, say, £2, $2, whatever the cost is. And then if tomorrow someone asks to buy 1 newspaper from you, you are gonna make £4 per newspaper. And then at the end of the day, say you bought 10 newspapers, but only 5 people showed up and bought from you, then you will have 5 newspapers at the end of the day, basically left over, but you cannot obviously sell them. No one is going to be interested in today's news tomorrow. So you are going to go ahead and return them and you are going to get this benefit of salvaging them, at least something you are going to get at the end of the day for the leftover ones. So then the question would be, if these are the problem parameters, how many newspapers you should buy today to go on the streets and then sell them tomorrow? It all depends on how many people will be out there willing to buy, right? So it's all about the newspaper demand for tomorrow. And the fact that we do not know exactly how many people will be out there on the streets, you will be wandering around, how many people will be willing to buy 1 newspaper from you. So you do not know exactly what the demand is going to be tomorrow. So then, of course, I'm now from Edinburgh. I need to put a Harry Potter picture here. So then if there is a magical news come to you and someone whispered to you saying that, you know what, I know exactly 10 people will be willing to buy from you tomorrow, what would you do? In order to maximize your profit, if you know that for sure 10 people demand will be equal to 10, you are going to order 10 so that you will sell them all, you will make the maximum profit. So you are not going to have any salvage for reduced cost, reduced profit. So you will make the best of the possible benefits, right? So if you knew exactly 10 will be the demand, you will buy 10. But we do not have this information. But then suppose you looked at, in order to predict what might be tomorrow's newspaper demand, you look at the historical data. Suppose you see exactly like you look at in the past week, what has been the newspaper demand on the streets. And then you realize that, okay, it looks very much like this perfect world. Day 1 of the last week, only 2 people wanted to buy. Second day, 4, so on and so forth. So if this is the past week's demand data, historical demand data, what would you say? How many I should buy? You will predict probably based on this trend that tomorrow the demand is going to be 16, you will buy 16. But then if you go further and then look at, say, 2 weeks worth of data, and then you see that, oh, it's not going to be 16 tomorrow because it seems like day of the week impacts demand and it has this recurrent kind of a trend. So what would you do then? So for tomorrow then, you will expect the demand to be 2. And if that's your prediction, you will like to buy 2. And more generally, there could be a different type of seasonality if you look further back in your historical data. Accordingly, leveraging more and more data, you can come up with better and better predictions for the future. And accordingly, that can inform your decision making much more. Okay, so now let me give you another historical demand data and let's work out this example in more detail. So suppose I have 5 years of data. Every day someone kept record on this street how many people bought a newspaper from someone selling. And then you look at this 5 years worth of data and then you see that magically there are only 3 numbers you see in the data. Or maybe this is the most, at least most often occurrences you see, say approximately or exactly, depending upon your data, you say that 25% of the time in the past 5 years, the demand has been 2, 50% of the days demand has been 4, 25% of the days in the past 5 years, the demand has been 7. So you fit this discrete probability distribution to your demand. So then we have this discrete distribution as your model of uncertainty for the newspaper demand. So then if this is what you believe, because you use a lot of data, you think that this fits to this uncertainty, demand uncertainty very well as a distribution. So now let's use this, assume that this is good enough of a model of demand uncertainty. Let's use it for decision making now. So this is the green box, right? I first build the uncertainty model. Now I'm feeding it, using it to make decisions. My decision, my question is how many newspapers to buy to maximize my profit tomorrow. So if this green thing is your discrete probability distribution that you fit into the demand using the data, how many newspapers you should buy? Should it be 2? Should it be 4? Should it be 7? Or it's none of these numbers? So that's the question. So if I try to slowly frame this as a mathematical model, here's how it's gonna look like, especially in a two-stage stochastic programming framework, this is how it's gonna look like. So my primary goal is to decide how many newspapers I should order, buy to sell tomorrow, but I'm making a decision now, how many I should commit to buy. So I am here, sitting here in the first stage, and I have this one decision to be made, how many to buy. But I have to make this decision without knowing exactly the demand, what is going to be tomorrow. But then in this green probability distribution, we actually created these demand scenarios. We specifically created 3 possible demand scenarios, these numbers, possibilities, with these associated probabilities of occurrence. So how many I should buy now so that tomorrow, whatever demand happens, accordingly, I will try to sell as many as possible. And if I have still some leftovers, unfortunately, I will salvage them to be able to maximize my profit. So we have 2 decision-making stages, but the primary, my only implementable decision is it belongs to this first stage, what I should do now. But then in order to improve this decision, to make a better informed decision there, I am considering my future decision, how many I could sell, how many I have to salvage in the future. And in between, I'm incorporating demand possible scenarios so that combining all these things in this framework, I will hopefully decide what is optimal, the best for me to buy. So then what is my objective? If this is my decision-making framework, how many I should buy here today now so that whatever occurs in terms of this uncertainty, accordingly, I will try to sell as many as possible in the second stage tomorrow so that I am maximizing my expected profit. So this profit thing is not deterministic anymore because there is uncertainty associated with the future. With, say, I decided to buy X many newspapers today and the demand is going to be, say, D in tomorrow. So then if with this probability, actually this demand is going to be equal to 2. And if I bought more than 2, I will sell 2, I will salvage the rest. If I bought less than, X is less than 2, I will only be able to sell 2. So let me maybe do a quick example. Say I decided to buy 5. So then if demand tomorrow occurs 2, I will be able to sell only 2 because only 2 people showed up and I will salvage 3. And I'm going to accordingly using the profit, the cost numbers, I'm going to calculate my profit. If demand happens to be 4 tomorrow, then I will, if I decided to buy 5, I will sell 4, I will salvage 1. If demand happens to be 7, I will be able to sell only how much I have at hand, 5, and then I will not salvage anything. I sold everything I bought, and I will calculate for these 3 scenarios my profit and multiplying these profits that I will incur in these respective scenarios with their associated probability of occurrence, I am going to calculate my expected profit. And this is the quantity I am hoping to maximize, expected profit. In other words, what is the single deterministic number I should make as a decision so that I am going to maximize this expected profit expression. And if you actually use such a possibilities, multiple possibilities of future called scenarios, demand scenarios, and you optimize your expected profit considering all these possible scenarios together, you are going to end up with the decision how many to buy, which is going to be significantly better than planning for only one possibility for the future. So I will take a quick pause here. Are there any questions? Is the example clear enough? Because now slowly we are going to build on this, and throughout the rest of the talk, I will try to rely on this example as much as possible. Any questions at all? All right. So just to give you some more realistic applications, I wanted to state a few things that I worked myself in the past. So for instance, there are plenty of applications of stochastic programming you can find in the healthcare domain. Few examples I would like to note here, again, the ones that I worked on myself, is for instance, hospital surgery scheduling. So suppose we have a pool of patients who need certain types of surgeries, and we have, say, a bunch of potential operating rooms to conduct their surgeries, and we have a horizon to assign their surgeries, some planning horizon, some days they can get these surgeries. So when to schedule these patient surgeries, which days, and specifically which operating rooms. Days could be also the specific times. But then what you don't know while you are making the schedule, you have to make the schedule, you need to announce it so that the staff and the patients, everyone will be ready when the time comes. But you need to make the schedule now without knowing exactly how long each surgery is going to take. But if it is a specific type of surgery, you have so much historical data that you can predict approximately how much each type of surgery might take, depending upon maybe patient characteristics. But again, nevertheless, you don't know it exactly. So, but you can fit a probability distribution for these uncertain parameters, create these future surgery duration scenarios, and incorporate them into your two-stage stochastic programming framework so that you are going to hopefully end up with a much more robust of a schedule. Because even if you plan and then a surgery takes a bit longer than the expected time, then you are going to be okay because you maybe put some slacks in between to protect against it, to hedge against such uncertainties. So this is again an example of two-stage stochastic programming, because in the first stage we are going to prepare the schedule, and in the second stage, when we get to observe in real time the surgery durations, they are revealed to us as we are conducting the surgeries. If certain things go over time, for instance, the end of the day, let's say you pass 5 p.m., some staff might still stay to do overtime, but you are going to pay them extra if they go overtime. But it's okay. You have some, what we call the second stage recourse decisions to still fix things that you haven't maybe decided the best. Another example from the healthcare domain is this kidney exchange programs. So suppose again you have a pool of patients. Each patient comes with a potential pair, and one person is willing to give a kidney for someone else so that their paired person, the sick person, will get a kidney back. So that your goal is to find these potential exchanges among the people of these donors and the recipients in the pool. But what you don't know exactly is if you pair up some people, whether they are exactly compatible. In other words, you could make some tests, and again, based on the patient characteristics and the test results, you have an idea how likely that this transfer is going to go through, but nevertheless, there is a bit of uncertainty, and you have to protect yourself against it. The last example from the healthcare domain I have on the slide is this radiation therapy treatment planning. You have a patient with a tumorous area that you are trying to send radiation beams to burn the tumor, but then these machines, you are sending a certain angled beam to a certain degree, but then it is not exactly how much each cell receives. There is a bit of uncertainty, especially if you think about patient lying to get the treatment. The organs or the patient might be moving, so that there is a bit of uncertainty for the how much dose is actually received, so that you can incorporate this uncertainty. Few quick applications from the transportation domain. One is, say, you are doing some bus or subway schedules, some timetabling application here, but you don't know exactly what the travel times would be in the operational day, but you have so much data, you can again fit a probability distribution, and you need to use them to make better, more robust schedules. But in real time, in the second stage, as you observe the traffic, the actual travel times, you could, of course, take some recourse actions to adjust the schedule a little bit. And another example is like, say, Uber type of a ride pooling example where the demand is uncertain. You don't know exactly at which locations how many people will need a ride. So you can model this and then incorporate it so that before you observe the demand, you can pre-position the vehicles to serve the potential demand much better. And then as the demand shows up, you need to match the customers to the vehicles, available vehicles. And the last example is this crowd shipping example. Crowd shippers are ready for delivering some orders for a company, but you don't know, it's a voluntary thing. You don't know exactly how many crowd shippers, in other words, supply you would observe. You might consider this type of uncertainty. Okay, so these were hopefully some motivating examples. Keeping them in mind, let's now do the math. Let's now formalize them. So we are calling this two-stage stochastic programming with the recourse because we also have in the second stage, after the uncertainty is realized, some extra decisions to be made, right? So as the name suggests, there is some stochasticity. So some of the parameters associated with your decision-making problem, they are not known exactly, they are uncertain. And in stochastic programming, the main assumption is we model them as random variables. So we fit probability distributions for these random variables. And as I mentioned already throughout the examples, there are two decision-making stages. The first stage is the most crucial one because these are the decisions we are after to make today, and we are going to implement them before we observe exactly what the uncertain parameter realizations would be. Once you commit to your first stage decisions, then in the future, these uncertain parameter realizations you will get to observe, as a result of which you might have some additional recourse decisions to be made in the future. For instance, how many to buy in the first stage, demand is observed, and then accordingly, I will decide how many I will sell and salvage. So then the objective is the first stage decisions are deterministic. How many I buy, I know this quantity, I'm deciding now. Accordingly, it is cost is a deterministic quantity. But for the recourse second stage decisions, because they depend on the potential scenario to be realized, we are minimizing, say, the expected cost of our decisions, just like what we did for the news vendor example. And why we care about two-stage stochastic programs, as I already mentioned, many of them, there are abundance of applications of this framework you can find. But just so you know, in case for future reference you might be interested, today I'm talking about two-stage stochastic programs, decision-making problems, but there are also the multi-stage versions of them. Say you are planning a production, let's say, plan for the whole week. Every day you need to decide how much to produce, or for the news vendor, maybe you need to decide every day of the week in advance how many to, or every day you need to decide for a week how many to buy. And in between uncertainty, the demand will be realized gradually over time. And your decisions, they need to be adapted to these observed uncertainties at every point. So if you consider these so-called multi-stage decision-making problems, then nevertheless, for solving them, two-stage models might be helpful because two-stage models are actually providing very decent approximations to multi-stage sequential decision-making problems under uncertainty. Okay, so now let's formalize them a little bit better with the help of some mathematical notation. So here's a generic form of two-stage stochastic programs. And as we said, we have primarily the first stage decisions denoted by this vector of x, and x has these deterministic set of constraints. Say maybe instead of just one product, the newspaper, I'm interested in buying multiple types of products. Say I'm interested in 5 different products to buy for tomorrow. So x is a 5-dimensional vector, and you might have some bounds or some constraints linking these different decisions that are put into this x and x set. And depending upon the x vector, this is going to be the cost of these decisions that you put into the first stage vector, decision vector x. But then this is not the end of the planning horizon. We will decide on this x, paying this cost, but then after we fix x, some uncertain parameters, here denoted by the vector omega, they are going to be revealed to us. For instance, for my 5 different products, this is going to be 5-dimensional demand vector. Uncertain demands will be revealed to us, and we will make further decisions in the second stage, and their cost will be represented by this function q of x and omega. And because omega is a random vector, we put this expected value so that from the second stage, we are trying to minimize the expected cost to be incurred. So more specifically, what could be this Q? In two-stage stochastic programs, for instance, suppose in the second stage, you only have some continuous decisions. And in fact, in the news vendor, you could actually make the how many to sell and salvage continuous decisions. So this Q function is basically what we call the recourse or value function, second stage value function. Say it could be represented as a linear programming model. So here in the second stage, I have this y vector of decisions to be made, and everything in this model could be all the coefficients, objective coefficients, or these constraint coefficients on the right-hand side. Everything might depend on the uncertainty scenario to be realized, omega. But importantly here, given the first stage decisions x and whatever omega is realized, you are trying to make the y decisions in an optimal manner. Okay, so this is my two-stage stochastic program. How can I solve this two-stage stochastic program? I'm trying to find what should be the x, and of course, in turn, indirectly, I'm also trying to decide y for each scenario omega, but there are some challenges associated with solving this model. First of which is this guy. The objective involves an expected value. So suppose this omega, my demand vector, has 5 possibilities, so 5 different dimensions. So I am talking about 5 products. W is, omega is the demand of product 1, demand of product 2, up to demand of product 5. So it's a 5-dimensional vector. And suppose for my demand, I fit a continuous probability distribution, say it is truncated normal distribution. So then what is the definition of expectation for continuous ones? It is actually, it's gonna be a 5-dimensional integral. So I'm trying to find the x that will optimize this integral in the objective. I have no idea how to solve this exactly. Even for the news vendor, super simple thing. If you have 5 different products, then this is something it's gonna be hopeless for you to solve exactly. So then we cannot solve this model as is with the expectation and the objective. We use instead approximation methods. We say, I'm not going to consider all infinitely many possibilities for these demands and then consider the integral. What I'm going to do instead is I will model my future with only finitely many possibilities. How many? K many. So I will create this calligraphic set K of possible demand scenarios for the future. So say this one is, it's gonna be bunch of possible demand scenarios. I'm gonna put each of them is a 5-dimensional vector here for demand realizations for my 5 products. Suppose I'm gonna put, say, 100 possible future demand scenarios. And I will say only these 100 can occur in the future. How you get these 100? If you have, say, this truncated normal distributions, you actually randomly sample from these probability distributions and create these random options. And then once you do that, what you can do is, once you refine yourself, confine yourself to these finitely many possibilities, this 5-dimensional integral, you can replace it with this sample average approximation. So you are going to say each scenario is, say, equally likely to occur, and then I am going to incur the cost of my decision x, say, under scenario, kth scenario omega of k. So you could actually replace the expected value, this difficult object to work with a finite quantifiable thing, which is this expected value over the scenarios, finitely many scenarios. And then there is some hope that we can solve this model. And this is when you replace this expected value with this so-called sample average, we obtain this so-called sample average approximation problem, and it is actually a large-scale deterministic optimization problem, still difficult to solve, but at least we can come up with some more efficient solution methods to solve this sample average approximation version. I'll skip that detail. So, for instance, suppose we confined our future into these k many possible future scenarios. So then this difficult blue problem we can equivalently represent as a one nice large scale though optimization problem. So what do? We leave here the X decisions, they remain as is, the first stage decisions, but the second stage decisions for future now, I have these k and k many possibilities for the future. For each of these possibilities, for my second stage decision vector y, I will create a copy of them. So this yk means which decisions you are going to take in the second stage if demand scenario k occurs. So you basically create these copies of these second stage decisions and say if they are supposed to be non-negative, each one of them is supposed to be non-negative. And there were some linking constraints between the first stage and second stage variables. You also create a copy of these linking constraints. And to simplify the notation, instead of using like say q of omega k, I simply put qk is the whatever the random variable realization objective coefficient realization under scenario k. So if I have finitely many scenarios, I can write down this single big optimization model. And how you might be interested in solving this is nothing but say a large scale optimization problem. You can find an appropriate optimization model solver and give this to your favorite solver. But suppose I have 100 scenarios, right? So I have 100 copies of these decision variable vectors. I have 100 copies of these constraint sets. So it's gonna be a very large scale thing. So if you just give this large scale model to a solver as is, you will probably struggle quite a bit. And just to give you an idea, this is an application from a call center stuffing and scheduling problem that I have worked on. Here, as you see, if I create this model using 100 up to 2000 scenarios, whether I can solve them. So none of them I could solve in a matter of 1 hour time limit. Of course, like these numbers will improve a little bit if you try with today's solvers, but the trend is gonna be more or less the same. And here, I cannot solve them, but nevertheless, with our solution methods, we get some optimality gaps, like what is the gap between our lower bound and upper bound on the true optimal objective value of my model. As you see, as you increase the number of scenarios in the model, you have a bigger and bigger gap. So you are struggling more and more to get decent solutions to this optimization model. So it is becoming hopeless. So instead of giving this big scale model to a solver directly, we usually rely on dividing this model into smaller and smaller, but many optimization models and develop these decomposition, so-called decomposition algorithms. So I will tell you a little bit about these decomposition algorithms next. So, of course, as I said, we are confined to these finitely many possible demand scenarios for the future. So suppose I have a two-stage stochastic program. The first stage decisions they are what they are, but importantly, my second stage model, remember what I will do under scenario K, given my first stage decisions, I will make some Y type of second stage decisions, and their cost will be denoted by this function qk of x. So in other words, our whole objective is minimizing the cost of x plus the scenarios, say scenarios are equally likely, times qk of x. This is our full objective. So everything about the second stage is buried under the definition of this thing. So let's start with this special case where this function is corresponding to the optimal objective value of a linear program. So all of our second stage decisions are continuous. All of the constraints and the objective expressions about this model is linear. So this is a proper linear programming model. What can I do then? That's my question. So then if the second stage model is in the form of a linear program, then you can apply this super successful algorithm of Bender's decomposition. So let me tell you how it works. First, I would like to show you why this decomposability structure we observe. Where is it coming from? And this is the structure that we exploit in designing these computationally much more efficient algorithms. So here is my full large-scale model. I could have given this to my solver, right? That model, but it is too big that I will fail. Here's how it looks like. So we have the first stage decisions, and here are the linking constraints linking the first stage decisions x's to the second stage decisions y1 under scenario 1, scenario 2, scenario k. If these scenarios occur, what I'm going to do in the second stage, right? So this is the full model, how it looks like. And now the key observation is, if I have a candidate first stage solution x, if I know what I might be willing to do in the first stage, suppose I fix the candidate x solution, then this is not decision anymore. If I'm fixing x to some candidate values of this vector, then these are fixed. In other words, you can push them to the right-hand side as constants. They are not decisions anymore. So then what do I have? Say I push them to the right-hand side, maybe I updated these values. So now the remaining optimization model, if you look at it carefully, what you will say is you are trying to minimize y1 up to yk vectors, and there are some constraints, but there are no constraints linking these blocks of decision variables. So if you are trying to, for instance, find what is the best y1 vector to do, you should just minimize this objective subject to these constraints, because y1 doesn't interact in this model with any other y vector. Similarly, if you're after y2 in this model, you should just pick this objective and these constraints. This green problem, you can solve it separately. Similarly, the last one, for instance, here, you could just solve the tiny blue problem, tiny green problem, tiny purple problem separately and put their solutions together. You solve this remaining problem. So the key observation again is, given an X candidate solution, the second stage copies of the decisions, they are not linked at all. So you could decompose this big optimization problem into many smaller, in other words, capital K many smaller optimization problems. That's the decomposition algorithm idea. And this is what you do. But while you are doing this, more importantly, we are going to use some special structure given that all of our y variables are continuous valued. So remember this qk, for instance, q1 was this objective value of the y1 decisions under scenario 1. So these qk functions, if you go ahead and mathematically analyze how they look like, they are actually nothing but super nice piecewise linear convex functions of x. If I give you an x, any qk of x function is piecewise linear convex, using which we can design an efficient solution algorithm for this model. And this is called Bander's decomposition. And in stochastic programming, this is known as L-shaped method. Why? Because if you look at all these basically blue, green, and the purple things, they look like an L, hence the name L-shaped method. Okay, so how does this method work? So we are trying to solve this problem in an iterative way. Rather than giving it as a whole as a solver, we will do this iterative algorithm. We will solve many but smaller optimization problems until we converge to the true solution of this full big model. So in the algorithm, what we are going to create is, the first thing we will create is this thing called a master problem. And this master problem is going to be concerned about making you an X candidate suggestion. And all the qk values, remember in the objective, I was supposed to have qk of x's here, but now I introduce an auxiliary variable eta k to represent that qk value. So I change my objective with the sum over the eta k auxiliary variables, and I need some constraints to encode this relationship that eta should be greater than or equal to qk, because at an optimal solution, when you minimize eta, it's going to be nothing but exactly the qk value. So how you would be able to get this relationship, because this qk is a complicated function, you will do these iterations to approximate this relationship between eta and q gradually over time with the help of constraints that we generate on the fly called Bander's cuts. So the algorithm works as follows. You initialize this master problem, say, with none of these constraints at the beginning. You solve this model. The model gives you a candidate X choice. And then you take this candidate X choice and you put it into your qk function value, which is nothing but a linear program. You fix the X candidate choice there, X hat, and then you give this small, very small linear program to a linear programming solver, and you solve it. And then the core, I don't have time to explain it, but once you solve this linear program with a solver, you can ask the solver to give you these so-called dual variables obtained at an optimal solution after you solve the linear program. And using this dual vector, optimal dual vector, you could generate this linear inequality. So this pi hat is a vector of numbers, it's given here. And here, this is an inequality linking eta k with the x. So it is giving you a better and better idea about what the value of the correct eta k should be, so that it is representing the qk value correctly. So you just repeat this loop, you get a candidate solution from the master problem, go ahead and fix it in this so-called sub-problem for each scenario k. For each scenario k, you solve this small linear program, ask the solver to give you a candidate dual solution, you generate this Bander's cut until your algorithm converges to the true optimal x hat candidate solution. Okay, so, but in general, if you just do this cutting plane loop, basically, this Bander's decomposition algorithm, it might take you a long time to converge, because these cuts that you generate, these guys, they are usually quite weak. And there are a bunch of ideas in the literature that you could do to strengthen these inequalities you generate over the iterations so that your algorithm will converge faster. And in that regard, one idea would be, if some of the x decisions, they are integer values, say some of them are supposed to be integers, some of them are continuous variables, then using this integrality information of the first stage decisions, you can improve these inequalities, so-called Bander's cuts. And in that regard, I will tell you a couple ideas how to improve these cuts based on the integrality information of the first stage decisions. And we can do this in two ways. One is we can strengthen these cuts in the master problem. The second way is we can first add some inequalities to strengthen the sub-problems, so that when the sub-problems are stronger, they generate better cuts for the master problem. Okay. And what is the idea? Just to give you a sense of where these things might be coming from, I will tell you one important inequality, what we call the veiled inequality from integer programming literature. So suppose, for now, forget about my stochastic program for a second. Let's just focus on this specific mixed integer set. So if I give you this specific set H, which is nothing but these blue line segments, this is my mixed integer set H. If I give you this H, then the observation pictorially, proof by picture, is that this inequality, this red inequality passing through these red points that I need to be on this side, it is valid for my blue set H. In other words, any point, blue point that belongs to set H must satisfy this red inequality. This is true, right? This is proof by picture, and this inequality is called MIR, mixed integer rounding inequality. You can sit down and have an easy proof of this, but even for the two-dimensional example, this is proof by picture, it's correct. So this is one observation, and there is a generalization of this idea. If I give you this type of a set now, where I have again a single eta variable, but a vector of x variables here in the set, and suppose in my H set definition, I have these two inequalities linking eta to the x variables. Using these, you can create a generalized version of a mixed integer rounding inequality. It looks like this. The details I grayed out, it's not important, but there is this inequality which is linking eta to x variables, and it is valid for my set H. In other words, any point that belongs to this set H that satisfies these conditions, it must satisfy this MIR inequality as well. So this is the idea that we are going to use to improve our Bander's inequalities, because these are exactly looking like their form are Bander's cuts that are generated in our decomposition algorithm. So whenever we have a candidate choice of Bander's cuts, we are going to apply this theorem to combine them pair by pair to generate these additional cuts to add to our master problem. So in the course of the algorithm, as I'm doing this loop, right, this iterative algorithm, I keep generating these Bander's cuts. So what we will do is, we have a pool of Bander's cuts that we generated in the past. At some point, we are going to say, I am going to pair them. Say, I'm going to pair this guy with this guy, put them into that formula, which will give me another inequality that needs to be satisfied by my solution. I am going to add this extra inequality, which is the MIR inequality, to my master problem to strengthen it further. So this is the idea. Like, as you do this loop, you generate from your scenarios bunch of Bander's inequalities, Bander's cuts. You are gonna basically apply the MIR formula to them one by one, pair by pair, and then you will generate these additional MIR cuts. So here's the same stuffing and scheduling example. Remember when I have given them for 100 to 5,000 scenarios as the big model directly to my favorite solver, here you see how much time I spent. After like 500 scenarios, I hit my time limit of 1 hour. I can solve none of my instances. However, if you do pure Bander's decomposition algorithm, it solves none of them. It is really bad. But if I strengthen my Bander's inequalities with the help of these MIR cuts, these are the solution times. I can solve all of my instances in less than an hour. There's some significant savings. Okay, you could do, I will just skip the details, but you could do similar ideas. So this is what we done before. This was our regular Bander's decomposition algorithm loop. And what we done is we did this MIR idea to generate some additional strengthening inequalities for our master problem. We got more to add and strengthen our master problem in this algorithm. The alternative is, as you are doing this loop, rather than generating more and more stuff for the master problem, you could actually generate more and more valuable information, some valid inequalities for the subproblems, so that the subproblems are getting stronger and stronger, and in turn, they will lead to better and better Bander's inequalities for the master problem eventually. So this is the second idea. And I will show you a bunch of examples. These are from different applications. For this one shows that if you add extra inequalities to the subproblem, that idea gives you the best results. It basically closes the optimality gap. You almost solve all of these instances. And another idea, another problem, this is a network interdiction type of a problem, whereas strengthening master problem more and more, it pays off for these instances better. So both of these ideas might be practically very helpful. Very quickly, I will just show you a bunch of other example ideas, different decomposition algorithms, just so you know that these things exist, but I don't have time to get into any details. So with the pure Bander's decomposition algorithm, what we had done is our QK problem was coming from a linear program. That algorithm is special for linear programming type of second stage models. If instead you have a generic form here, but your first stage decisions X's are all binary, then there is this special case of decomposition algorithm called integer L-shaped method, where you still do this master and sub problem loop. It is exactly the same thing. Master gives you a candidate, you pass it to every scenario K sub problem, solve it to calculate this QK, and you return some cuts to strengthen your master problem gradually over time. But now in this setting, the cuts are different. Rather than these Bander's cuts, you are using another form of called integer L-shaped cuts. And more specifically, the cuts look like this. Again, the cut is importantly linking your auxiliary eta k variable to the x variables. Everything else you see is a number. It's a parameter in the cut. But the form of the cut is different, and it is validity why you are allowed to use this form of cuts is because of this structure that all of them are binary. If you have something super general, then there is this most general version of a Bander's decomposition called logic-based Bander's decomposition. This one, it is super general, but you need to do the work to come up with the form of your own valid cuts to use in the algorithm. So you need to do more work. If you're interested, I have a paper as this healthcare application that I mentioned, operating room scheduling for patient surgeries. In this example, using the specific structure of our QK model, where we have these binaries, whatnot, we came up with this form of a cut, and then we said we sat down and then proved that these are valid cuts that we can use, and if we only use these cuts, you are going to converge in this loop type of an algorithm to the true optimal solution. So another structure, interesting structure, is this time I am forcing myself to consider only binary second stage decisions and also binary first stage decisions. If this is how your two-stage stochastic program look like, then you might be able to do something completely different. So in this case, we have some technology where this binary program, with the help of these things, graphical structures called binary decision diagrams, you can reformulate this binary program through this decision diagram idea as a pure linear program. It's going to be a bit larger, but then because this became linear program, you can use pure Bender's cuts that we've seen already. So for instance, just to give you an example, this is a binary program. This is called a knapsack problem. I have these 4 binary variables, 1 constraint, and this objective. So this is one way to model this so-called knapsack problem as a binary program. But there is this graphical representation of this basically feasible set. I don't have time to detail. If anyone is interested, I can do it offline. But we could graphically represent the feasible binary solutions to this as these root to terminal paths in this graphical structure, using which we can obtain an equivalent formulation. And instead of using this binary program, I can use this linear programming version. This is a larger thing because here, instead of 4 variables, you have 1 f variable per arc that you see in this graphical structure. It's a larger model, but it is not binary anymore. It is purely LP. And if I'm instead using this LP, I can do the pure Bender's decomposition algorithm. And what we done is we basically, I don't have time to explain for the specific example. This is the example that comes from this paper. We have generalizations of this in our recent paper where we can leverage binary programs for some a bit more general 2-stage stochastic programs. And if you do this idea, this is for these binary type of problems, this is the most general logic-based Bender's decomposition integer L-shaped method. If you use R cuts, then this is the performance profile. The higher is better. You could improve solvability of these models with the help of these decision diagram-based cuts or approach. You can solve many more instances. So finally, maybe in a minute or 2, I will give you the most maybe general thing you might be interested in doing, especially if some of you is interested in machine learning, incorporation of it with optimization. This is a good example. So this approach, which we called neural two-stage stochastic programming, you can handle most generic case of two-stage stochastic programs. So this could be most notably any type of model, if you like. It could be nonlinear. And the idea would be, using some learning approach, you are gonna learn through supervised learning the form of this function. Especially what you will do is you will generate some training data, some candidate x's and some candidate accordingly qk values, and you will apply supervised learning to learn this function value. It might be a very complicated function. For instance, for the most nonlinear case, it's maybe very complicated, but if you learn it as a neural network approximation, then this neural network approximation of this QK function, you can write it down as a mixed integer program and combine it with the first stage, and you can obtain a surrogate approximation model. So the idea is anything general in the second stage, with the help of neural networks, you can represent them as a mixed integer program and apply some of the algorithms that is amenable to second stage being mixed integer program. The final thing I would like to let you know, FYI, there is also this scenario reduction techniques, which might be very handy, because how we started is we said solving two-stage stochastic programs, they are very difficult. Hence, we do this sample average approximation using finitely many possibilities, but the more possibilities you use in your models, better decisions potentially you will obtain. So instead of 100 scenarios, maybe you would like to use thousands of scenarios. But then the trade-off is using 1,000, you may not be able to solve your models efficiently despite using a decomposition approach. So you would like to use smaller number of scenarios where the scenario reduction techniques might be handy. And in the scenario reduction literature, there are 2 approaches. One is you only use the distribution of the demand, for instance, to do the reduction. Other one is you do more work and use some problem structure to do the reduction. Here's an example on the right. Suppose I have these 4 possible scenarios. Now I'm using a different notation, but suppose I have these 4 possible scenarios, and in the distribution-based approach, you first cluster these scenarios with respect to their closedness. And then for each cluster, say this is your cluster 1, this is your cluster 2 as a result of your clustering model of these vectors. Then from each cluster, say you pick the center. So then if you do the scenario reduction, instead of using these 4 blue scenarios, say you are going to use these two vectors as your scenarios in your stochastic programming model, and hopefully it's going to lead to good enough solutions. In the problem-driven one, you need to solve some optimization problems, especially some single scenario optimization problems, and solve another clustering model. But this could lead to, as opposed to these guys that comes from the first approach, this might suggest you to use these two scenarios instead of the four. So they lead to different things, and I can tell you that this is shown to work usually much, much better than the first approach. Okay, just to conclude, I hope you have enough of an idea what type of applications, anything pretty much, stochastic programs can be helpful for decision making under uncertainty. And importantly, these models are super difficult to solve. So we do sampling based approaches, but even for solving the sampled versions of these models, we need to do some clever algorithms to be employed, especially decomposition algorithms. And there are so many ideas of different structures of decomposition algorithms and even how to improve them more and more. Thank you very much.
Thanks a lot, Merve. It was very clearly structured and very inspiring and useful talk for us, I believe, especially for those who are interested in.